I'm Seung-Kyu Choi from Sungkyunkwan University. And today I'd like to introduce about our recent work, SparkCube, hardware combining sparsity and quantization for LLMs. As LLMs grow, running them directly on devices like smartphones or desktops become more attractive. On-device inference offers fast response, lower latency, and stronger privacy. But to make this possible, we need compression and also hardware that can run compressed model efficiently without reversing the compression. We start with a full-size LLM that's too big and slow for most devices. There are many compression methods, but we focus on quantization and sparsity. These methods help reduce the model size without losing much accuracy. In quantization, there are two main types, weight-only quantization and weight activation quantization. And for sparsity, there are three methods, unstructured, structured, and semi-structured sparsity. Our objective was to focus on weight-only quantization and semi-structured sparsity and to design hardware that supports both natively. Like we said, we focused on hardware support for weight-only quantization and semi-structured sparsity. Specifically, in weight-only quantization, we convert 32 bits weight into 4-bit integer while keeping inputs and outputs in full precision. In semi-structured sparsity, we enforce a fixed pattern like 2 out of every 4 weights being 0, which make it easier for hardware to exploit. By supporting these two compression techniques in hardware, we can run LLMs more efficiently on resource-constrained devices. Before we combine these two techniques in hardware, we first look at their impacts on model accuracy. Here, we show the perplexity of dense floating-point 16 models as our baseline references. Perplexity is a standard metric for LLMs. Lower means better predictions. Applying either 2 for sparsity or weight-only quantization with integer full leads to a small accuracy drop, especially in smaller models. When we combine both techniques, weight-only quantization and 2 for sparsity, this drop becomes very similar to this drop in accuracy. It's a bit larger than using either one alone. However, as the model gets bigger, this drop becomes very smart to ignore. This motivates our design of SparkCube, a hardware solution that combines both techniques to maximize efficiency while keeping accuracy high for large-scale LLMs. We aim to design hardware that combines both techniques, but existing hardware platforms aren't ready to support them effectively. First, existing hardware only supports floating point by floating point or integer by integer, not mixed precision floating point by integer. Second, integer weights need to dequantize back to floating point, which adds overhead. Third, semi-structured sparsity isn't natively supported, so its benefits are often lost. That's why we propose SparkCube, a new architecture that addresses these limitations and enable efficient execution of compressed LLMs. Even though we want hardware to support compressed model directly, most existing systems still follow the standard full precision setup. In a standard transformer model, both the inputs and weights are usually in floating point. So our matrix multiplication operations in the linear layers and the attention block are done as floating point, floating point. If you look at the zoom-in attention block, every layer takes a floating point input, uses a floating point weight, and produces a floating point output. It's a completely floating point only pipeline. And what happens when we quantize weights to 4 bits? Existing hardware still only support floating point, not mixed precision, floating point integer computation. So we have to dequantize integer weights back to floating points, adding overhead. That means we can't fully benefit from compression without native integer weight support in hardware. So we decided to support floating point by integer computation directly in hardware, which became the starting point of SparkCube. We designed a new Mac unit that takes floating point inputs and integer weights without conversion so we can skip the quantization and actually benefit from quantization. But even if linear layers use floating points integer computation, not all operations can. Matrix multiplications in attention blocks still use floating points by floating point computation, so we also need hardware that supports for floating point computation. At the core of any accelerator is the matrix multiplication unit. Our design focuses on enhancing the MXU to support both quantization and sparsity at the same time. This is our baseline MXU app using a historic array for floating point computation. It works well for full precision LLMs, but becomes a bottleneck when weights are quantized to integer. That's why we need something more flexible module. Integer 4 weights are streamed in, and floating point inputs stay inside the PE. Each P performs floating point by integer and accumulate in floating points. This module knows the quantization needed. And last, this is MXUSI module, our final design. It extends MXUI with structure changes to support end-to-end semi-structure sparsity. So here we show the overview of SparkCube. SparkCube combines MXUF module for floating point by floating point and MXUSI for integer weights with end-to-end sparsity. This enables efficient support for both MR and linear layers in LLMs. Typical historic arrays follow either weight stationary or input stationary data flows. For example, Google TPU use weight stationary. This slide shows how weight stationary works. Weights stay inside PEs and input flow across. It fine for dense model, but with semi-structure sparsity, zeros are still processed wasting cycles. Now let's look at the input stationary data flow. In this setup, the inputs stay fixed inside the PEs and the weights are streamed in. For dense model, this isn't much different from the weight stationary approach because our weights are using anyway. But when we compress weights like in semi-structure sparsity, we can skip the zeros and only fit in non-zero weights. That means fewer mag operations and we can actually see real speedup. And that's exactly why we choose input stationary historic array for our architecture. Now that we've seen why input stationary is a better fit for sparse weights, and let's dive deeper into how this works inside the MXUSI modules. Here's a simplified view of two PE rows in our input stationary design. While this helps skip zeros, new challenge arrive when we apply end-to-end sparsity, which we will walk through next. Let me walk you through a simple example. We multiply an 8x2 sparse weight matrix with a 2x1 dense input vector. This produces an 8x1 output, and we'll use it to highlight execution time completes. This slide shows how 2 to 4 sparse gem works using an input stationary historic array. Each weight row follows a 2 out of 4 sparsity pattern, meaning only 2 weights are non-zero. The inputs stay fixed in the PEs while the weights move horizontally across the array. At each step, the P performs a multiply and accumulate operation between the input and the incoming weight. The result is a partial sum, which gets passed down to the next P in the following row. As weights continue to move and max are computed, the final output building up gradually through these partial sum accumulations. Here's the sample we've been using. Let's focus on output 01. It's computed from 2 zero weights multiplied by inputs I0 and I1. Now, if we apply model compression and remove these zeros, 01 can't be computed anymore. So even if sparsity helps reduce the model size, we still need to ensure our outputs like 01 are properly handled. In the baseline design, output like 01 can be missed when our corresponding weights are zeros. To fix this, we add a skipping path that ensures our outputs are accumulated properly, even with sparsity. This guarantees correctness is preserved without losing any outputs. Now, this example also shows another key issue. In the uncompressed model, output O2 accumulated weight B multiply I0 and weight C multiply I1. There are no conflicts. But with 2 to 4 complete compression, weight B moves to second slot and weight C to the first, shifting their timing. Due to systolic flow, C arrives 1 cycle later, so both B and C try to update O2 at the same time. So this creates a data hazard. We can't accumulate both to P2 in the same cycle. Let's take a closer look at what happens when the compressed weights are fed into the same input stationary architecture. The initial setup looks the same as before, but as the cycle goes on, 2 conflicts start to appear. As we move from cycle 1 to cycle 2, a conflict appears in input stationary 2 to 4 sparse execution. Here, P2 needs to be processed by 2 PEs at once, which cause contention. This shows that sparse weights need smarter handling of partial sum timing and routing. To resolve the earlier conflicts, we add an inter-P buffer between rows. This buffer stored partial sum temporarily, so they don't need to be processed right away. It prevents collisions and supports faster timing under sparse weights. We added an inter-P buffer and skipping paths to solve earlier partial sum conflicts. But now, multiple partial sum may arrive out of order, and we need to decide which path to take, accumulation path or skipping path. To handle this, we use sparse pattern indicator called SPI. For example, if a weight group has non-zeros at index 0 and 3, the SPI generator produces metadata, A path for accumulation and S path for skipping paths. When this group enters the buffer, SPI guides P0 to accumulation path and P1 go to skipping path. The same logic applies for P2 and P3. This way, partial sum are routed correctly, even under semi-structured sparsity. These slides show the high-level architecture of SparkCube. MXUF handles standard floating point operation, mainly used for attention block in MERS layers. And MXUSI supports floating point input and integer weights with end-to-end sparsity and is designed for linear layers. Together, they enable efficient execution of both dense and sparse computation in LLMs. This table summarizes the area and power of the 3 MXU types used in SparkCube. Compared to MXUF, MXUI reduces both area and power by about 25% by removing 4 precision multipliers. MXUSI adds some overhead, 43% more area and 49% more power, but supports end-to-end sparsity, giving double throughput. And the RTL implementation of MXUSI modules in publicly available as part of our architect. This slide shows the relative inference time with different MXU configurations. The results are normalized to the baseline setup with 4 MXUF. As we reduce the number of MXUF, attention blocks slow down since they rely on floating points, and can't exploit sparsity. But adding more MXUSIs speeds up linear layers that benefit from quantization and sparsity. All in all, inference time depends on the balance between attention and linear layers. For example, in a PT66 billion model, using 1 MXUF module and 3 MXUSI module reduces latency by 26%. This shows that for large model around 1 billion parameter and above, SparkCube delivers real performance gains. And this chart shows relative TOPS per square millimeters, again normalized to our baseline for MXUF setup. For smaller model, we don't see much gain because they rely more on matrix multiplication from attention blocks, which only run on MXUF modules. But as model get larger and linear layers start to dominate, the advantage of MXUSI becomes more obvious. For instance, on OPT66 billion model, The setup 2 MXUF module and 2 MXUSI module improves area efficiency by 33%. And on Bloom 7.1 billion model, we see up to 53% higher efficiency with 1 MXUF and 3 MXUS in setup. So our MXUSI module doesn't help everything. It gives area benefit when the workload is right, especially when there's more linear computation and sparsity to exploit. In energy efficiency, measured in TOPS per watt, just like we saw with area efficiency, the benefit of MXUSI becomes more noticeable as model size increase. Smaller models still rely heavily on matrix multiplication, but once we pass 1 billion parameters, the linear layers dominate, and that's where MXUSI shines. For example, OPT 13 billion model achieved a 51% increase in energy efficiency when using the 1 MXUF and 3 MXUS sync setup compared to the baseline 4 MXUF setup. Here's how SparkCube stacks up against another prior work, Figna. If you look at the number here, one thing immediately stands out. With SparkCube MXUSI, we achieve 1.79 higher area efficiency than Figna. That's a huge jump in terms of how much performance we get per silicon area. And even more impressive is the energy delay product called EDP. SparkCube MXUSI achieves a 5.27 lower EDP than Figna. In other words, we are not just faster, we are way more energy efficient at the same time. All in all, SparkCube delivers much better compute efficiency without sacrificing performance or energy. So to wrap up, here's the key takeaway. SparkCube improves LLM inference efficiency by using a hybrid architecture that combines MXUF and MXUSI. This allows us to handle both dense and sparse workloads efficiently, whether it's matrix multiplication in attention or linear layers with quantized weights. By doing so, we can fully exploit quantization and structure sparsity, achieving better performance, energy efficiency, and area efficiency, all at the same time. Thank you for your attention.
Okay, thank you for the great talk. So, do we have any questions? Okay, it's no more. I have one, actually I have several questions, but can you go back to the evaluation slide for the, for any one of the,
Here?
It might be, okay. So which means that the best configuration will change depending on your target models.
Yes.
So therefore my question is that, should you assume to use the FPGA, or will you use some kind of the ASIC chip? So which means that when you change the target model, how can you find the best configuration? So it depends on the model, and model characteristics will change over the years.
Yes.
Okay.
In our work, we just focus on not configurable architecture, and just how we fix architecture MXUF and MXUSI modules different configuration, and when we change the configuration, we had these results for many large language models. So in our future work, we make a configurable architecture for LLM models. So yes.
So is there no takeaway for this kind of the evaluation study? Okay, that's fine. Okay, and another my question here is that you mentioned that input stationary is good for this kind of the accelerator.
Yes.
How about the other previous work? Do they use the weight stationary so far? Is this your novel approach in this work?
I think for this work, input stationary is best techniques for make hardware architecture for LLMs support quantization and sparsity, but when we use another comparison techniques or another hardware setup, so input stationary is not best techniques, I think. But in this work, input stationary is.
How about other approaches? Do they use the with stationary so far? Okay, that's fine. I have another several questions, but we don't have enough time. So thank you again for the great talk, and we will. Oh, sorry. I have really narrow scope.
I have one question on the same slide.
Oh, yes.
The slide shows us about like performance varies around configuration.
Yes.
Then my question is, so what configuration?
This configuration for.
What is the
yes.
size of each array and how many arrays? So in this case, you are assuming that like so you actually have 4 different arrays and
Yes.
2 MXUF and 2 MXUSI.
Yes.
It seems that that combination is better in almost all cases. Right?
Yes.
Then it does not depend on the size of array, or like why don't you use like number of more arrays?
First, our configuration of MXUSI and MXF module for SparkCube. Every MXU module have 64 by 64 PE.
Okay.
Okay, and we have 4 MXU in SparkCube architecture for this work. And because of this configuration, we check difference with previous work like Figma or another post LLM accelerator. So we choose configuration like this.
So does it mean that you use like 50% of utilization of array for like, so when you are performing some integer and floating, then you use only 2 arrays, and for other ones then you have only 2 arrays. So how do your utilizations? So in your proposed approach, then how do your utilization is only 50%?
Yes.
So, okay. But still it is better, like if we have 4 MXUF and
Yes.
we do not actually we use dequantization, like
Yeah. Yes.
then you can use the whole architecture fully,
Yes.
right? But still you are saying that like 50% of hardware utilization is better
In the quantization LLM models.
without if your proposed approach is
yes.
not use dequantization, right?
Yes.
But you actually sacrifice hardware utilization by 50%,
Yes.
right? So if you add the dequantization block and we use full MXU minus F hardware block,
Yeah.
then you increase the utilization 100%,
Yes.
right? So, but your proposing says that like, so 50% utilization is still better
Yes.
in terms of inference speed. Is that right?
Yes.
Okay. So
Okay.
I understand that your proposed approach will be better in terms of energy consumption, for sure.
Yes.
But my question is about inference time. So
Inference time.
yeah, inference time only. So if we
Oh,
use
it's not.
100%.
It's not for our LLM models. For you said no dequantization in models.
So if we use
Yes.
dequantizer and we use only floating point arrays only,
Yes.
right? Then you can utilize 100% hardware.
Yes.
Because all matrix multiplications or linear operations are floating point operations.
Yes.
But your proposed approach seems like hardware utilization will be only 50%.
Yes.
So that is my question. So still, okay.
Yeah, you can talk offline there. Okay. Okay, thank you.
Yes.
Okay, let's move to the next talk. Okay, next talk is the other PS from Seoul National University. The presenter will be the Xiaomi. So we are actually behind, so you can start.
Good afternoon, everyone. My name is Jaume Mateo, and together with Professor Bernard Egger, I will present this paper, Adaptative Data Partitioning to Parallelize CNN Invariant Resource on Constrained Hardware. And these days, as we know, that AI is more popular than other models, so we try to move CNNs to edge devices for privacy, and the main problem of this is that these devices usually have low memory and low processors, so what we try to solve is dividing this so the inference is not underperform and we can still keep the privacy on those devices. We try to focus on heterogeneous devices since usually we try to use anything that we have in our labs, and we try to do the partitions in an efficient way so it doesn't take forever to compile. Here is a simple example of what we try to do for the motivation. Usually we have different devices, and those devices have different speeds and different characteristics, so we try to divide it, and this can generate some data transfer between them when we try to communicate between them, and we try to find the best partition between all of the devices. Some of the challenges that we found during this research was the complex network graph path and which order do we have to process, or how should we cut the path to process in a better way. In our case, we use a greedy path approach. The other problem that we find is the exponential search space. As we know, as the number of devices increases and the size of the layers also increases, those search spaces become exponential. So it's really difficult to represent and to fit all the all the space in a memory. To do that, we created a procedural partition tree structure. And the other problems we found out is how do we search this search space, and because usually it takes a lot of time. So the optimizations that we applied is alpha beta pruning together with some dynamic programming. When talking about these networks, we also have to take into account that they have different operators so each node is characteristic by some operators, normalization, convolutions, and another type of operators. So we try to use the main characteristic of these and generalize them so we can find groups that we can divide easily. And finally is how do these devices communicate? Usually the two solutions that there are centralized or decentralized. We opted for decentralized because as the number of devices increases, the overhead is a big problem. So our main contribution is a flexible technique for different types of hardware together with an efficient search space that it takes a reasonable time to search with a good solution. And finally, an end-to-end layer search that will take into consideration all the layers of the network. Since we talk about our decentralized system, we wanted to compare with the other with the other projects that they had decentralized options. This was BBGraph and Edgeflow. The key differences between those related works is that BBGraph uses a greedy approach where it divides all the layers into the same sizes, and it keeps all the layers separated so it doesn't take into account the information of previous layer or the next layer. For Edgeflow, the key difference is that it uses linear programming to search the vast search space, and also it takes into consideration direct layers, but it doesn't keep forward to the next and next layers. In our case, we use a recursive approach where we start searching the first layer, then we include these results into the next layer and keep going up and down through the network until we find a consistent solution that is good. To do that, we require some hardware specifications like the processing speed, the bandwidth, and the network information, for example, the size of the output, the size of the inputs, the weight sizes, the dilatation, stride, etc. Here is a simple example of our algorithm. We can divide our algorithm into 3 steps. One will be selection, search, and backpropagation of the results. In the first example, we have the selection until we get to the terminal node, which will be the layer 0. When we get to the terminal node, we do a search space between layer 1 and 0, and then we backpropagate, as we can see in the number 2, to the previous layers, the partial results. In the first one, we can see that the red arrows will denote that there are word results, so they don't have to be stored when we do the backpropagation. And when we do the next selection, we do again the selection, search, and we compare both of the previous results to see which one is better on the fourth one. If the result is not better, we just can skip the next search and go to the previous layer and keep doing that up and down until we reach the last layer of the path. As I mentioned before, the challenge of how to represent these enormous possibilities is we did a procedural search space that will construct the partition on demand. This tree search is divided in 3 levels. The first level will be the layers, second level will be devices, and the third level will be the start and the end of the partition. If we look closely at in the red selected partitions, the example is presented on the right bottom. Here we can see a direction size output that we can see that the starts at 0 and 3. This is the first partition for the first device, then it goes to 2 and 6 for the second device, and 6 and 9 for the third device. This tree is not all kept in memory, but it uses also it uses copies of themselves, as we can see on the top layer 0. When we select one distribution, it will ask for the stored tree, and it will be the same on all of them. For the optimizations, first we will start with dynamic programming. As we were doing the search, we saw that this tree will keep repeating itself multiple times, as we can see in different colors. In here we see the red colors will be one subtree, green color another one, and the blue one, it will be another one. This keeps repeating recursively the more devices that we have. One key thing to notice is that these subtrees, it will always start when the third level is a start point. And the next, using the previous optimization of the dynamic programming, we use the pruning method that it will avoid already partial results that we know from previous subtrees, so we can skip many of the results and not do all the calculations, and this is how we achieve the vast improvement on time. So for the evaluation, we use Raspberry Pi 5 and 4. We created a simulator using the PyTorch and their distributed library. For the network, we choose old and new ones, more simple, more complex, and smaller and bigger. As we can see, biggest one is BGG, smallest one will be MobileNet B2, and the more complex ones and newest as the Inception B3 and Hardcore NAS. For the experiments, we run the compilation in maximum of 5 times. This was the case for BGG 16 usually, and to validate it, we run 100 times each configuration independently. We tried 2 and 4 nodes approaches. In the 2 nodes, we can see that the data transfer is really improved. All of the results are normalized to edge flow. And then we can see an improvement in the inference time around average of 15, being the best ones in the simplest networks and a little bit worse in the more complex due to the greedy path search. For 4 nodes, we see the same trend, around 15, 18% of improvement. However, the data transfer is a little bit worse due to the number of synchronization between all the devices. So now for the pruning, as I mentioned before, the pruning is one of the most important parts to keep the time reasonable. Here we can see in base log 10 that as we increase the number of devices and the freedom of the partitions, these numbers become immensely big. Finally, some conclusions. We found we presented an efficient algorithm to keep search space in a reasonable time with a good solution. And some of the ongoing work that we are trying to do is LLMs with the transformers and RNNs with the recursive path. And finally, one final thing that we would like to improve that other papers also doesn't do is how to find a better past search. Thank you for your attention. Any questions?
Okay, thank you for the great talk. Any questions?
Thank you for your intriguing talk. Does your work cover transform operations or reduce operations?
Transformers, it doesn't. With another future work.
Then I'm curious. I'm curious what portion of the overall latency is attributed to that kind of operations.
Like which one?
Reshape or transform or reduce operation.
We don't have an actual like analysis of operator by operator. Usually the most these operations, because they are all connected to one device, usually we don't consider that, but we try to consider it later. One of the other future work is using division of fully connected networks using weight division.
Oh, are they crucial for gaining performance?
Huh?
Are they crucial?
What do you mean? What are the future?
The operations including reshape or reshape, transform, or reduce operations.
Usually, I don't fully understand what you mean as if they are crucial, but we don't usually reshape them. We usually allocate them in memory. If you mean that, I don't fully grasp what you mean.
I mean that we have lots of operations regarding transforming shape.
Yeah.
And it seems like that your work does not cover this kind of operations, right?
But this is depending on the network, isn't it?
Yes.
Yeah.
So I would like to know what portion of the overall latency is attributed to this kind of operations, because if they are not crucial, then we don't have to take care of it, right?
Yeah, usually those reshape and everything, it's just treated as any other operator. So we don't have an analysis of operator by operator. So I cannot fully answer these questions of how is good in performance or not.
Thanks.
Okay, any other questions? Okay. Oh yeah.
Okay, I have a very quick question. You've compared your work to previous approach, but how much reduced your latency compared to just running on a one device solely?
We don't have this here, but usually the problem is sometimes they don't fit into one device, so we cannot compare it even against those.
But maybe a mobile net is very small to run on a single device, like Raspberry Pi.
Yeah, we don't have the results here.
Okay, thank you.
Okay, so we are out of time. So thank you for the talk again, and we will move to the next talk.
Yeah, it's a small room. No, I'm supposed to pass the mic.
Yeah, I passed the mic.
Yeah, but it's a small room, so it's not necessary for me to.
Okay, let me introduce the next talk. The next talk is the Graphitron, a domain-specific language for FPGA-based graph processing accelerator generation. So presenter will be Xing Miao from Institute of SKLP. Okay, you can start.
Thanks for your introduction. Good afternoon, everyone. My name is Zhang Ximiao, and I'm a PhD student from Institute of Computing Technology, Chinese Academy of Sciences. Today, I'm happy to present our work, Graphitron, a domain-specific language for FPGA-based graph processing accelerator generation. This work is a collaboration with Hong Kong University of Science and Technology, Guangzhou. Now let's get started. Here's the outline of my talk. I will start with background and motivation. Then I will introduce the design of Graphitron and describe the workflow of its compiler. Then finally, I will present the evaluation results and end with our conclusion. Graphs are everywhere. Since Leonard Euler used the graph to solve the 7 bridges problem, graph has demonstrated exceptional expressive power and is widely used across a broad range of disciplines, including social network, finance, transportation, and knowledge graph. As a result, graph processing has become a fundamental building block in many large-scale data processing systems. Graph algorithms present 2 key challenges. First, they involve a huge number of irregular memory accesses and have a poor locality. On CPUs, this will cause frequent cache misses, resulting in low cache efficiency. Second, because of the power load distribution of the graph, there is severe workload imbalance. On GPU, this will lead to warp divergence, where threads in the same warp follow different control paths and serialize execution. As a result, general-purpose computing engines suffer from low hardware utilization and poor energy efficiency when running graph-related workloads. FPGAs offers a promising alternative. They support custom memory and execution paths, have high parallelism with low power consumption, and provide fine-grained scheduling. These traits make them ideal for graph processing on the edge side, such as smart camera, V2X network, and industrial IoT. For example, in V2X systems, vehicle-to-intersection communication forms a road graph where local edge computation helps with the cooperative path planning. However, despite of the advantage of FPGAs, given the diversity of graph algorithms, designing efficient accelerator remains very challenging, particularly for those without expertise in FPGAs. Many FPGA-based graph processing frameworks have been proposed to lower the programming barrier by providing easy-to-use interfaces. These frameworks typically rely on a pre-built accelerator template or hardware overlays that incorporate various hardware optimizations for generating the accelerator. However, this tight coupling of programming models, processing paradigms, and accelerator architecture can limit the flexibility and lead to suboptimal performance of the generated accelerator. Firstly, only algorithm capable with the provided programming interfaces can be expressed in the framework. It will limit the expression scope of the algorithm. Moreover, the pre-built accelerator template adopts a fixed processing paradigm. For example, edge-centric or vertex-centric ECP or VCP to integrate the specialized hardware optimization. These approaches may perform poorly for some of the algorithms. For example, ECP is effective for algorithms such as PageRank, where all vertices are active. However, it struggles with BFS, which only activates a subset of vertices, resulting in considerable redundancy. This limitation underscores the need for a more flexible method of generating FPGA-based graph processing accelerators. In the CPU or GPU domains, Graphite is a well-known DSL for parallel graph processing, which decouples graph algorithm descriptions from their optimization strategies with easy-to-use algorithm and scheduling language. The algorithm language makes it flexible to describe the algorithm, and the scheduling language expands the optimization space by manually indicating the optimization strategy. Inspired by it, we seek to bring this idea to FPGA domain, enabling flexible algorithm expression while ensuring efficient hardware generation, and finally, make efficient FPGA-based graph accelerators available to everyone. However, the challenge in designing such a DSL lies in balancing abstraction with the customization, which means on one side, different from Graphite, which exposes the optimization to the users, our DSL should allow users to describe algorithm without dealing with any low-level FPGA details, especially considering that users may not be familiar with FPGA at all. On the other hand, removing those manual optimization requires the compiler to infer and apply hardware optimization automatically to the generated accelerator, which is challenging given the diverse computation and memory access patterns in graph algorithms. Next, I will introduce our design of Graphite. This figure illustrates the development workflow of Graphite. From a high-level user's perspective, they can flexibly describe the algorithm by customizing operators to vertices and edges in the graph, and then orchestrating their workflow through writing the Graphite code. During programming, users do not need to specify any FPGA-based optimization. Then the compiler of Graphite produces HLS-based FPGA accelerators. The front end ensures the code correctness by grammar checks and resolving ambiguous issues encountered in many FPGA-based graph processing frameworks. Subsequently, the middle end conducts semantic analysis and infers suitable hardware optimizations, annotating these optimizations as text in the intermediate representation. In the backend, Graphite integrates this optimization on the accelerator kernels to generate graph processing accelerators. Finally, for system integration, the compiler generates the host program, which is responsible for graph partitioning, workflow control, and FPGA device management. Let's start with the DSL design. The DSL is an object-oriented programming language. It abstracts the vertex and edges as data types to instantiate the graph objects. We take Graphite code for BFS as an example. Firstly, users should specify the graph file and construct the vertex set and edge set as graph objects at the beginning of the code, and define all the data structures, which is also known as properties related to these objects. Secondly, user can define some operators for these objects to describe the procedure of graph algorithms. Finally, user can describe the whole graph algorithm workflow by orchestrating these predefined operators through calling the provided API. In this way, GraphitTrain can naturally support VCP, ECP, or their hybrid processing paradigms by customizing operators to the edges and the vertices. For example, GraphitTrain code for BFS with hybrid paradigm is shown in the listing. It implements seamless transition between the VCP and ECP based on the runtime frontier size. From the compiler side, the front end constructs an abstract syntax tree and generates the front end IR. Our front end involves a self-developed lexer and parser tailored for handling graph-centric object abstraction, such as vertex, edge, and their property, thus directly mapping these concepts without excessive pragma or hints. The middle end of the compiler maps these concepts to the target FPGA and adds some hardware optimization tags. In detail, the compiler allocates the appropriate memory space for these objects, then automatically assigns memory units and their channel ID to the objects, enabling the FPGA to efficiently allocate the memory and manage the pointers for transferring data to hardware kernels. Besides, the middle end infers and adds some hardware optimization tags to the operators, including the memory optimizations for graph properties and the parallel and the pipelining optimization for the operator. The parallel tag is added to the operator automatically. It will use to unroll loops to maximize the data parallelism. To determine the optimal unroll factor, the compiler sets the parameter as the number of memory channels where the corresponding object is allocated. For the pipeline tags, we rely on the HLS tools to automatically determine the minimal feasible initial interval for instruction level parallelism. Besides, GraphitTrain incorporates optimizations to graph properties to improve their access efficiency. The burst read and write module has much higher sequential bandwidth than the normal read or write to the memory. So we utilize this module to read or write properties. However, the properties related to different objects exhibit distinct access patterns. Edge-related properties are typically accessed sequentially, whereas vertex-related properties involve a lot of random accesses. Consequently, we adopt a tailored memory access optimization based on the differences. For the edge properties, we simply utilize the burst read or write to maximize the sequential bandwidth. For vertex-related properties, we need to fully utilize the loaded data by the burst read or write. So we allocate a dedicated cache module with FPGA's Ultra RAM to enhance the data reuse. Additionally, for vertex properties holding random writes, we implement a shuffling module before burst writing to convert the random writes into the sequential writes and facilitate conflict-free operations for higher bandwidth, further improving the memory throughput. Finally, this figure illustrates the overall background framework of the generated kernel by the backend. Instead of relying on the built-in accelerator templates, it employs a generic architecture comprising basic modules designed to accommodate a broad spectrum of algorithms. For each operators, the properties of related graph object are first streamed from FPGA memory into the cache module. Then the vertex or edge process module perform the user-defined function to generate the update streams. If the output is not marked as shuffling, the update stream is directly written back to the memory. Conversely, the stream is further routed to the stream duplicate module, and it is duplicated, sliced, and distributed across different PE. In each PE, the shuffling model reorganizes the update stream and filters out the unnecessary updates. Subsequently, conflicts are resolved by the REW module, and the redundant updates are aggregated by the reduce module. The resulting updates, which are sequential, are then stored into the cache. Finally, the updated properties are streamingly written back to the FPGA memory. Finally, here comes our evaluation. We implemented Graphite on Xilinx LVU'25 FPGA. We tested 6 graph datasets from different categories. We tested 5 different graph algorithms, including 3 graph traversal algorithms, BFS, SSP, PageRank, and 2 emerging algorithms, personalized PageRank and graph attention. We compare against standard GP, state-of-art FPGA graph framework, which is a representative benchmark for the performance, and a naive HLS implementation, which is a benchmark for flexibility. As we evaluated, both Graphite and standard GP significantly outperform the naive HLS implementation, primarily due to their integrated optimizations. Furthermore, Graphite consistently achieves better performance than standard GP for BFS and SSP. The reason is that Graphite enables users to implement the accelerator with hybrid kernels of both VCP and ECP paradigm, reducing a number of redundant edge traversals. However, its performance in PageRank is slightly lower compared to standard GP. This gap arises because standard GP only supports returning the cumulative sum of differences between old and new PageRank values. In contrast, Graphite develops the flexibility to individually record these differences, so introducing some more overhead. The most significant performance improvement stem from the memory access optimization. We designate Graphite variants that individually integrate burst rate, shuffling, or caching, respectively. And we show the result. The result indicates that incorporating only a single memory access optimization yields limited performance gains. This occurs because optimizing only one memory access pattern leaves other a bottleneck. As for flexibility, due to the reliance on a fixed programming interface, standard GP cannot support algorithms such as PPR and graph attention. In contrast, Graphite achieves average speedup of 71 and 240 times over the naive HLS implementation, respectively, demonstrating a strong performance combined with high flexibility. As for the design productivity, when writing a new algorithm, standard GP demands modification across at least 5 different files, while Graphite enables users to implement a graph algorithm with fewer than 100 line codes. Besides, standard GP's configurations often require extensive FPGA-based expertise, and Graphite empower even inexperienced users to efficiently customize the graph acceleration. To summarize, we propose Graphite, a DSL for FPGA-based graph processing. It enables flexible, high-level graph algorithm and compiles to optimized hardware designs. Thank you for your listening. I'm happy to answer your questions.
Okay, thank you for the great talks. Because of the time limitations, we will just get the only one question. Any questions so far? Okay, so I have actually several questions, but only one question will be like this. Oh, sorry. There are two different FPGA companies for the Xilinx and the Altera, right?
Okay.
So yeah. So are your optimization techniques independent to the hardware vendors or not? So which means that if you target another different FPGA from the Intel Altera devices,
Okay.
so will you share some of the your optimization techniques or not?
So now I just focus on one vendor. Just
But in general.
yes, but I think if you want to target another platform from different vendors, you can just modify the backend of the FPGA, I think.
Yeah, that is my question. So which means that do you have any specific optimization in the backend, considering the backend hardware or not?
Yes, I think some of the automations are special for.
Okay, thanks.
Okay, thank you.
Okay, thank you again. Okay, let's move to the next talk. Okay, so next talk will be the modeling and verification of sigma delta neural networks using satisfiability modular theory. Okay. The presenter is the Shasendra Das from the Indian Statistical Institute. Okay, you are ready? Okay, let's start.
Thank you for the introduction. So, hi everyone, I am Shasendra Das, and today I will present our work on modeling and verification of sigma delta neural networks using satisfiability modular theory. Okay. So, in modern times, AI has transformed the world around us via multiple breakthroughs through diverse domains like computer vision, natural language processing, and reinforcement learning. And today we have like multiple different types of neural networks for specific domains. Like we have CNNs for the image processing and transformers for the NLP domain. So in summary, there are some requirements in real world requirements, and from that requirements we get some input output pairs, and we feed it to the machine learning algorithm, and that gives you some artifact. So the challenge here is how can we verify these systems? Because the opaqueness of these systems is a challenge, and the traditional quality assurance techniques losing the steam. So the question is, can things go wrong? And the answer is yes. If there are small changes to the correctly handled inputs, then that can lead to unexpected or erroneous behaviors. And also there are some types of adversarial attacks. So in 2014, an intriguing property was observed that when the left image is fed to a neural network, it is classified as a panda with 57.7% confidence. But when we add a small amount of noise with it and fed it to the same neural network, it gives a classification of gibbon with 99.3% confidence. So the small perturbations of inputs lead to misclassification. A more serious concern is when we just add 11 white pixels with the traffic light image, it is misclassified as a kitchen oven. So what are the challenge? First is ensuring the robustness of these ML models before deploying, and the second is energy efficient neural networks like spiking neural networks used in safety critical systems must be rigorously verified to prevent the unforeseen accidents. So our objective is to bridge the gap between the energy efficient neuromorphic computing and formal robustness guarantees, ensuring the sigma delta neural networks can be deployed with confidence in real world applications, and also to establish a robust framework for formal verification of SDNNs, the most prominent model in the neuromorphic computing. So here is our contributions. We first propose a method to encode the SDNNs as satisfiability modulo theory, SMT constants, enabling a comprehensive and expressive representation of SDNN behaviors. Second, we leverage the SMT encodings to perform the rigorous verification and robustness analysis of the SDNNs. And next, we present our experimental results on temporal versions of the benchmark dataset MNIST to demonstrate the validity and correctness of our SMT-based model. So, before going to the sigma delta neural network, we just define the verification problem once. So, let's suppose this is a SDNN, sigma delta neural network, and there is an input space x bar and there is an output space y bar. We first define a property, input property P over the input space, and also we define a output property Q over the output space. So, defining after this, the verification problem in case of SDNN is as follows. For a SDNN n from x bar to y bar and an input property P of x bar and an output property Q of y bar, thus there exists an input x naught bar and output y naught bar such that x naught bar satisfies P and the output y naught bar satisfies the property Q. Where P of x bar satisfies the, so basically that characterizes the input we are checking, and Q of y bar characterizes the undesired behavior for those inputs. And if this problem has a negative answer, that means it is unsat or unsatisfactory, that means the property holds. And if it gives a positive answer that is satisfactory, that includes a counter example. So now the SDNN, so it is the most prominent model in neuromorphic computing. It is energy efficient like SNNs, but the only difference between SNNs and SDNNs are, instead of using the binary spike, it uses real values. And so SDNNs are a specialized type of neural network that process the changes in activation between consecutive inputs rather than decomputing the entire activation. And it has two key mechanisms. One is temporal difference or delta and temporal integration or sigma, which focus on detecting and accumulating changes in the input over time. So here is an example. So the first A is the original network where the traditional weight multiplication and the W1x is the weight multiplication and H1x is the activation functions. Next, we define the temporal difference and temporal integration operation, and we introduce this in the original network. That will give you the temporal difference network. You can see like here are two algorithms in the bottom, algorithm 1 and algorithm 2, corresponding to the delta and sigma. The delta algorithm just computes the difference between two consecutive inputs and report it, and while doing so, it just like rewrites the previous input with the current input, and on the right hand side the sigma operation, it is just accumulating the changes over time. Now in picture C, you can see that is a rounding network where the round operation is introduced before the weight multiplication, and merging this B and C will get the sigma delta neural network where both rounding, sigma and delta operations are included. Now next we define the adversarial robustness problem in SDNNs. So for a classification problem with n classes, we first design SDNN n with the n number of output neurons. Then an SDNN n is trained for classification in adversarially robust when the small perturbation to a given input sequence gamma naught does not lead to a change in the predicted class y naught is equal to the majority voting of eta naught, where eta naught is the output of the SDNN. So now depending on this, we encode a formula that is P of gamma and n of gamma is equal to eta and naught of Q of eta, but P gamma is the it states that gamma is a perturbation given the input sequence gamma naught, and Q eta states that the majority voting of the output eta should be equal to Y naught. So given SDNN's unique event-driven processing and temporal dependencies, traditional verification methods for the dense neural networks may not be directly applicable or in this case. Then we have the SMT, and with its capability to encode the discrete state transitions and sparsity constants, it emerges as a compelling framework for analyzing these SDNNs under adversarial and safety critical conditions. So now we introduce the SMT encoding. So SMT is a very powerful formal verification technique that extends the Boolean satisfiability by incorporating different mathematical theories such as linear real arithmetic. So SMT encoding of a given SDNN involves encoding the execution semantics of the internal and the output neurons. So for doing this, we first introduce some real variables. So XIT denotes the values in the input layer for all the neuron ni at time t. Then Wij, this denotes the weights between the synapses for the adjacent neurons ni and nj. Then RIT is the output of the round operation. DIT denotes the output of the delta operation, and YIT denotes the output of the sigma operation. So this after introducing those real valued variables, we made the constants. The first is the initialization. So initially all the things are initialized to zeros. Then we write down the quantization constant. Then this is for the delta operation. Then the sigma operation, and lastly we have the output constant. So collecting these 5 constants, we define the SMT encoding of denoted as Fn to the given SDNN like this. Next we do a interval bound derivation where we propose a lemma along with the proof that states that for an SDNN, consider consecutive delta and sigma neurons at layers I and the consecutive layer, that j, equal to I plus 1 respectively. Now let XIT and delta IT be the input and the output of the delta neuron, and sigma jt is the output of the sigma neuron at time t. Then for all t greater than equal to 1, if we assume that XIT is bounded as alpha and beta, then the sigma jt has a lower bound, that is summation over I wij times alpha plus t times bj, and it has a upper bound, that is summation over I wij times beta plus t times bj for all t greater than equal to 1. Then following this lemma, we introduce the bound constants, that is for each neuron we use the SMT to design to encode these bounds, and we just put this bound, extra bound, with our previously the vanilla SMT, and we get this encoding of the neural network. Now the temporal data processing by SDNNs. So what do you mean by temporal data? So basically it refers to the data that is recorded or observed over time, where the order and time intervals between the observations are important. So unlike static data, which represents a snapshot of at a single point in time, temporal data captures how the values evolve over a sequence of time steps, and it can be processed efficiently using the delta and sigma modules, capturing changes rather than the raw values, making them energy efficient for time dependent applications. So next we introduce the temporal MNIST. So temporal MNIST is a temporal version of the MNIST dataset that is useful for testing models that needs sequential data, like in our case SDNN, or in the SNN, that is spiking neural networks. It emphasizes on the spatiotemporal relationships by using the minimum L1 distance to choose the next image in the sequence. So here is the algorithm in small details. The first we create some buckets where each bucket contains images corresponding to specific digits. So there are 10 digits, 0 to 9. So 10 buckets are there based on their labels. Then randomly initialize a buffer of length 1000 by selecting 100 unique images for each digit from the corresponding bucket. It ensures no duplicate images within a bucket are added to the buffer. Then we generate the sequences by repeatedly choosing the images with the minimum L1 distance to the current image. So what we are doing, for each sequence, we first randomly select an initial image in the buffer, then replace the current image in the buffer with a new random image from the same labels bucket. Then in the third step, we find the closest image in the buffer using the L1 distance and appends it to the sequence. And we repeat these 3 steps until the desired sequence length is reached. And now what is the level of each of these sequence? So it is determined by the majority voting of the images labels. So here are some sample images from the temporal MNIST of sequence length 16. You can see. Now the formulation of the adversarial robustness in SDL. So we use a specific type of definition for the adversarial robustness in our framework. It says that for a given non-negative integers delta, small delta and epsilon, the delta perturbation of a temporal input sequence gamma naught with temporal window t refers to changing it by at most delta frames within D, where each frame can change by at most small delta many values within the frame, where each value can change within a frame by at most plus minus epsilon. So basically we have 3 hyperparameters, or basically we have 3 parameters: capital delta, small delta and epsilon. So for example, if delta equal to 7, small delta equal to 400 and epsilon equal to 100, so this is the original sequence from the temporal MNIST. After perturbation, this goes to this, and the perturbations are in that indices 7, 3, 8, 5, 2, 15 and 11. Now after doing this, we get the end-to-end framework where there is a pretend SDNA comes to our framework, and we encode that first. Then also the input property P gamma and other input constants are coming, and the output property is coming. All these things will go into a constant solver, and the constant solver will give you either 2 outputs. It is either give you a SAT or it will give you an answer. So here are some results of on the temporal MNIST dataset we got. So we run 3 distinct experiments based on the parameter values, capital delta, small delta and epsilon. The first experiment shows that if there is a complete frame drop, so where 1 or more frames within the temporal window are removed entirely, and all the values in each of these removed frames are set to 0. So these are the results with different variable sequence length 4, 8, 16 and 32. Interestingly, if you see, like in all the when the temporal window length is small, both the vanilla SMT and the SMT with interval bounds perform like equally, but when the length increases, the SMT with interval bounds have like overtaken the vanilla SMT. The second experiment shows that partial frame drop with complete frame perturbation, where a subset of values within the chosen frame is set to 0 instead of removing the entire frame, evaluating the network's response to partial occlusion. And the third experiment shows that partial frame drop with partial frame perturbation and partial pixel perturbation, where selected pixels within the dot frames are perturbed within a predefined range epsilon, further testing the network's robustness. So more results are in the paper. So in conclusion, we first define a symbolic SMT based model for adversarial robustness verification of a given SDNN, and we also show that how simple bounds can be derived on the sigma units that can expedite SMT solvers, and we also define the adversarial robustness property motivated by the video stream processing. So here are some related works for our paper. Thank you for your kind attention.
Thank you for the great talk. We will get only one question. Any questions? Okay, I have one question. Okay, it looks like you used a really small data set like the MNIST, right? So, and can you use the larger data set or not? If not, is there any constraint for constructing the SMT-based model or constructing the large SDNN or something like that?
No, basically, we are currently working on the larger data sets. So this SDNN is used in different architectures. So it is we are currently working on a NVIDIA's architecture that is called PilotNet. So that uses this SDNN architecture, and it has a big data set. So we use our framework, integrate with their data set, and there is also the convolution operation is there. So we integrate those things, and we will submit like our
Okay, it's just problem of the time. Okay, and how long it will take for the verification?
For this work or the
Just this one.
we give a 1 hour like timeout period. So all the results are within 1 hour.
Okay, it looks reasonable. Okay, thank you. Okay, let's move to the next talk. So we have 2 remaining talks, but they are short. Okay. The next talk will be the Juju, a streamlining free RISC-V vector extension with arbitrary register grouping compilation support. This is the WIP papers. And the presenter will be the Shiwi Su from Shanghai University. Okay.
Hello everyone. I'm Siyi Xu from Shanghai University. Today, I'm honored to present our work titled "Use of Streamlining Free RISC-V Vector Extension with Arbitrary Register Grouping Compilation Support." Let's start with the motivation behind ZooSurf. In vector ISAs like AVX, SVE, and RVV, streamlining is commonly used to handle varying vector lengths. For example, AVX relies on software level streamlining, SVE uses predication like where8, and RVV uses hardware controlled register groupings. In RVV, LMUL as a specialized parameter that determines how many configuration number registers are grouped together in one register group. RVV only supports a power of 2 register grouping, which bring 2 merger changes. The first one is efficient register utilization. The second one is tail processing inefficiencies. We can see the right side image. First, when the vector length is relatively short, maybe it only needs 3 registers, RVV might still allocate more than necessary. For example, if LMUL is set to 4, RVV will assign 4 registers, even though only 3 are actually needed, because RVV uses a rigid power of 2 grouping. So the unused register space ends up being wasted, Secondly, when working with longer vectors, we often need to split the data into chunks. This is known as strip mining. The changing counts as and the leftover data, known as tail element, is usually very small. However, we still assign 4 register groups to store them. As a result, these groups are mostly underused, leading to inefficient register usage and lower performance. To address this, we introduced RISC-V vector extension that is have strip mining free. We add asymmetric instructions to handle ultra long vector efficiently without repeated loop-based strip mining, and ZooServe removes the rigid register grouping limitation of RV, allowing flexible allocation based on workload needs with the arbitrary register grouping. And then finally, we integrate LVM-based compilation support, enabling for utilization of ZooServe feature. LVM allows defining fixed length vectors in the front end using X vector type with the attribute, but the LVM backend imposes a limitation. The core MVT class relies on the simple value type enum, which can represent only up to 256 types. This constraint prevents support for arbitrary length fixed vectors, which ZooServe requires. Therefore, extending or bypassing this limitation is issue for enabling ZooServe's compilation support. Now let me briefly walk you through the ZooServe compilation workflow. To support ZooServe's features and overcome compilation challenges, we designed a custom 5-step pipeline. Besides built-in functions mapping the core parts is the step 3. We apply a splitting parts to break down intrinsics into smaller parts, and then inserting delimiters to help with register grouping. This ensures each split part is easy to manage and fits ZooServe's hardware model. During over register allocation, we use those delimiters to make sure the splitting virtual registers are assigned consecutive physical registers, maintaining proper grouping and alignment. And then we perform assembly coalescing parts in the step 5, where consecutive user instructions are merged back together. This removes redundancy and restores the performance of the original high-level code. Overall, this pipeline ensures user
for the long session. So we will have the last talk. So the talk is about the toward the macro aware C2 Rust transpilation.